Good afternoon. We'll give a few minutes for people to join, and then we'll get started. Thanks everyone for joining us today for the CARUS webinar series, What You Need to Know, Odor Control with Permanganate. I'll be your presenter and host, Darren Scott. A few items to go through. Attendees will be kept in listen-only mode. If you do have questions, enter them into the questions pane over on the side of your computer, and we will get to some of the questions depending on how much time we have left. If we don't get to your question during the presentation at the end, I will follow up with an email and a response back to you for the questions you've done. If you would like a PDF of the slides and/or a recording of today's presentation, please feel free to email me directly at darren.scott@carusllc.com. So I'll be your speaker today. I've been at CARUS for 26 years. I'm the Senior Technical Service Specialist. I'm a chemist by trade. I work with our municipal industrial remediation customers, doing jar testing, trials in the field, working on equipment. I'm a member of American Water Works Association, the Water Environment Federation, the American Chemistry Council. And like I said, I'm a chemist by trade. My degree is in chemistry from Illinois Wesleyan University in Bloomington, Illinois. So to go over a brief outline of what we're going to cover today, we're going to cover odor control with permanganate. We're going to start out in the collection systems where the wastewater starts, and then move in toward the plant itself, and then to the headworks, and then into the plant in solids dewatering. We'll talk about odor surveys. We'll talk about the many different treatment options that you might have, and then we'll have case studies for each of these different applications. So one of the big things is, what is odor, right? How is it formed in your system, both out in the collection system, at the headworks at the plant, in the watering process itself? What are the reasons that you would treat for it? It could be as simple as meeting the OSHA regulation for hydrogen sulfide. It could be customer complaints or odor complaints from people near the plant or near that sanitary sewer. And then what are different things you can do in your treatment plant, but we'll focus on permanganate itself, specifically on how it can remove odor compounds like hydrogen sulfide and mercaptan. So wastewater systems are very complex, lots and lots of different parts, lots of different pieces moving the wastewater from a person's home to your wastewater plant. So you can generate odor throughout that process. So out in the collection systems, you have pump stations / lift stations collecting wastewater before it pumps it downstream through a forced main. You can have gravity sewer discharges where you can have odor complaints too as well. So those are all places you're collecting the wastewater from homes or from businesses or from schools, and you have a chance to collect and concentrate the odor at those places. It moves through the collection system, obviously downstream towards your wastewater treatment plant, and you have your headworks at the wastewater treatment plant where you do screening and grit removal where you might have some odor control issues. You then have your clarification processes, your sludge settling in your plant, and then typically, depending on the size of the plant, you might do dewatering with a belt press or a centrifuge to dewater to have biosolids that you're either going to go out and do land application with, or you're going to send to the landfill as waste. Throughout this process, probably the biggest thing that most people associate with wastewater generally is nuisance odors. So both hydrogen sulfide and mercaptans can cause rotten egg odors or different types of odors out there in the system. And typically those are the things that people are going to notice. So they'll smell that rotten egg odor, they'll smell the funky mercaptan smell, and they'll call in to complain. And it can be in the collection system, it can be coming from a manhole, a lift station, just the sanitary sewer, the gravity sewer itself. If it runs through a downtown area, you can get those complaints. And then obviously that complaint can happen at the headworks of the plant or people that are nearby the plant if they can smell those odors drifting off the plant site. Some of the other things we don't think about as much in wastewater, though, is equipment corrosion. So hydrogen sulfide is super corrosive. It will form sulfuric acid, so it can corrode the concrete, the iron pipe that you have out there in the distribution system, so you can destroy that infrastructure in the collection system itself, and then you can actually destroy some of the infrastructure in your plant as it corrodes the metals of the plant too if the hydrogen sulfide gets too high. One of the things we don't think about all the time until we actually physically see it happening, like you flip over a manhole cover and you see the concrete and the rungs and everything kind of corroded. And one of the other things you might see out in the collection system is you will, as you're collecting that wastewater, if you don't have a good pre-treatment program, tell people, not to dump grease down the drain, you can see some grease buildup out there in lift stations and pump stations that can impact them too as well. Now, tons and tons of different odors in wastewater. Depends on what kind of compounds are going. Typically for municipal wastewater, it's usually hydrogen sulfide rotten eggs, which we'll talk about. But if you have other kinds of discharges, so industrial discharges or other kind of food industry, just any kind of industry in general that can discharge other types of organics to the system, you might have some different odors that you might see. So you could have something like skunk, rotten cabbage, fishy. Depending on what's going on, you might have ammonia. You might have fecal, decayed flesh. So all different types of odor compounds that are out there. But typically there's kind of some that kind of filter to the top. Generally, the big one is right here in the middle of this chart, hydrogen sulfide, which has the very distinctive smell of rotten eggs. And its odor threshold, you can see, is very, very low parts per million, 0.00047. So most people will be able to start to smell it at that very, very low level. So parts per billion levels, they can smell it. Typically, we're concerned with it at parts per million levels, and you'll see that on the OSHA standard. A lot of the other compounds you hear, you'll do special testing. So maybe you have rotten egg, but maybe you have a different specific odor. So you can do some odor testing and determine, is it a mercaptan? Different mercaptans have very different smells that are out there. But whole range of compounds you can have. So if it is a different odor that's not rotten egg, it could be a mercaptan or one of these other organic compounds that you can smell. The big takeaway here is that odor threshold wise, all these compounds well below part per million in the part per billion level area where that you can actually smell them. So like I said, those are kind of some of the weird odors with the mercaptans. Hydrogen sulfide is probably the biggest one. And then depending on what's going into the process, you might generate some ammonia at the treatment plant or out in the collection system. Along with those gases, you could have carbon monoxide or carbon dioxide, or in a processing or treatment plant where you're breaking down biosolids, you could generate some methane. So that's sometimes when you go by a wastewater plant, you'll see the methane where they're flaring it off with a flare. You'll see the same thing sometimes as well at landfills, where they're generating methane gas from the breakdown of the products in a landfill, and they'll have the methane flare. And then kind of the common other things we have in the atmosphere, oxygen, nitrogen, and hydrogen. The big one though, probably by far the most common at most places it's causing the odor complaints, is going to be hydrogen sulfide. So it's a colorless gas, so you don't see it in air. It has a very distinctive rotten egg odor. The issue with the rotten egg odor is as you stay in an environment with hydrogen sulfide, that rotten egg odor deadens your sense of smell. So initially when you walk into an area or initially when you start to smell the rotten egg odor, you'll be able to smell it directly. It'll be pretty repugnant at that point in time. The longer you stay in that environment, it starts to deaden your sense of smell and you don't smell it anymore. So you think the odor has gone away when truly it hasn't. And that can be dangerous because you don't know that you're still in that environment. The other part there as well is when you leave the area, that hydrogen sulfide can get in your hair, can get on your clothes, it can get on your equipment, and when you leave the area, as your sense of smell comes back, you'll notice that sense of hydrogen sulfide as it kind of comes off your clothes, comes off your equipment. So you'll notice that you're stinky when you leave the site as your sense of smell comes back. Hydrogen sulfide also water soluble. So a portion will be soluble in the water, and then the portion that strips out will become atmospheric hydrogen sulfide. It's extremely toxic. You're going to see the OSHA chart for it here in a slide for how dangerous it can be in the environment. It's one of the things that you would measure for confined space entry as well. And then on top of that, at different levels, it can be corrosive. So it mixes with atmosphere and moisture to form sulfuric acid, which can corrode metal, concrete, just all sorts of equipment. You'll see some pictures of that as well. And then depending on the concentration, if it gets high enough, it can actually get into the explosive range. The big risk besides all the odor complaints from hydrogen sulfide is its toxicity spectrum, specifically called out by OSHA. And you can see down there, most people are going to smell it below a part per million. Like I said on that earlier chart, some people can smell it down to parts per billion. It's pretty offensive odor when you get up to about 3 to 10 ppm, which can cause a lot of rotten egg odor alarms. A lot of safety monitoring is going to be usually pegged to 5 and 10. So 5 to let you know that you're at a level, and 10 to know you're at the OSHA standard. So the OSHA standard is a 10 ppm time-weighted average during an 8-hour shift. So over that whole 8-hour shift, you want to be under 10 parts per million of hydrogen sulfide. You are allowed a peak for 10 minutes in an 8-hour shift of up to 50 ppm. In that 10 to 50 ppm range, if you're in that, or you're in a spike area where you get exposed to it, some people it will cause headache, some people it will actually cause nausea as well. But as that level increases, it's also deadening your sense of smell so that you can't smell it, in addition to giving you the symptoms. Obviously, as you move up this list, it becomes much more dangerous. It can cause respiratory tract irritation, olfactory paralysis, and then you can see imminent life threat at 300 parts per million. What ends up happening with hydrogen sulfide is it displaces the oxygen out of your blood, and generally what will happen is you'll pass out, and then if you're not out of that environment, since it's displacing the oxygen, you will die. Typically, one of the things with hydrogen sulfide that happens in local news stories or online, a couple times a year, there'll be incidences where people have died from hydrogen sulfide exposure. There'll be where they went into a tank or they went down into a sanitary sewer and they didn't do monitoring and they were exposed to hydrogen sulfide and the person passed out. And obviously, if they couldn't get them out there, they didn't have a way to rescue them, they're going to pass out, they're not going to get any oxygen, they're going to die. It also happens in farms where they have large manure pits or areas where they'll generate hydrogen sulfide as well. Somebody goes below grade, gets caught with hydrogen sulfide, passes out, and since there's not a way to get them out easily because they didn't plan for it. So that's one of the things why you almost always when you see confined space entry, you'll see monitoring for hydrogen sulfide along with oxygen levels. If somebody's doing sanitary sewer work, like a municipal worker, they'll have monitoring as well for that if they're below grade because of the concern of lack of oxygen and the hydrogen sulfide there. So almost always, anytime you're seeing that, you're going to see at least 1 or 2 people outside the pit and 1 person in the pit doing the work so that they have a way to monitor to make sure if there's an issue, they can get that person out of the pit safely with equipment. So you don't want to mess with hydrogen sulfide. Definitely, you can look it up online on Google or other websites and see that there's several deaths a year based on hydrogen sulfide exposure out there across the US in different applications. So how does hydrogen sulfide form out there in the collection systems? So the formation of hydrogen sulfide is going to be, there's sulfate in the wastewater itself, plus there is organic material as well. So all the stuff that we dump down the sewer. And then you have anaerobic bacteria. The anaerobic bacteria are looking for oxygen, so they chew the oxygen off of the sulfate molecule and they generate dissolved sulfide in solution. That dissolved sulfide has an equilibrium, so part of it's going to stay in solution and then part of it's going to strip out of solution in the headspace. So the headspace in a tank, the headspace in a gravity sewer, or in the headspace of a lift station, or just the headspace going through screening or gritting or grit removal. And then you're going to have that rotten egg odor generated, and then that hydrogen sulfide can mix with moisture to form sulfuric acid. Everything's there for those sulfate-reducing anaerobic bacteria out in your collection system and then into your plant. They thrive at low oxidation reduction potentials. Most wastewater is pH 6 to 9, so they've got a perfect environment. Wastewater typically warmer than the outside atmosphere here in the cold north, although now we're warming up, so temperature is always going to be warm. And then if there's no dissolved oxygen, the anaerobic bacteria predominate in that case and will generate a lot of hydrogen sulfide. So what does that look like out in the collection system? In this case, you've got a gravity sewer here. So you've got the pipe wall, you've got some bacteria growing a slime layer on the inside of the pipe itself. You've got the wastewater passing through the pipe. If there is sufficient oxygen, so you have a high dissolved oxygen level in the wastewater, greater than 1 milligram per liter, typically then you won't have much dissolved sulfide in the wastewater. The bacteria that are going to predominate are going to be aerobic, they're going to chew up the oxygen, and they're not going to generate anything else. What ends up happening, though, is as that dissolved oxygen level drops, because as the bacteria pull the dissolved oxygen out of the wastewater, those bacteria are going to start to look for oxygen in other sources. So what ends up happening is, once they run out of dissolved oxygen, they're going to start chewing up on the sulfate that's in the wastewater itself. Sulfate's always in excess out there in the wastewater itself, so they'll start chewing on the sulfate, so they'll chew the oxygen off of it, and they'll generate dissolved sulfide into solution. So now you start to increase the level of dissolved sulfide in the wastewater itself. And then as that sulfide level builds, it's in equilibrium in the water itself and the atmosphere above it. So some of it's going to start to slowly come out of solution. Now, there are ways to pick that up. If you shake it or cause turbulence with that wastewater, so it falls into a pit, you're pumping it, so you're aerating it somehow, you're going to strip more of that dissolved sulfide out of solution and force it into the atmosphere. Once it gets into the atmosphere, it can mix with moisture to form sulfuric acid. And what ends up happening is, as that sulfide forms sulfuric acid, it corrodes everything it comes in contact, so metal, concrete. It hits the pipe wall, goes down the pipe wall, back into solution, and now you end up back at sulfate again, and then the cycle starts over and just kind of keeps repeating itself time and time again. So one of the things with hydrogen sulfide is it is in an equilibrium. So generally between pH 6 and 8, you're going to have a portion of it as dissolved sulfide and a portion of it that's going to go atmospheric, that you can see here with the percents of totals. Right at pH 7, it's roughly going to be a lot, about 50%. So right, 50% is going to be in solution, 50% is going to try to go atmospheric, especially with some turbulence. One of the ways you can treat for hydrogen sulfide is to raise the pH up. What that does is it does not remove the dissolved sulfide, but what it does is it traps it into solution. So you can see on this chart, if I raise the pH up and I get up to about pH 9, somewhere between 9 and 10, I'm out of the area where the hydrogen sulfide, the H2S, is. So I'm going to trap all of the sulfide in solution at that higher pH. So you can pH adjust your wastewater and try to trap it in solution. Now what happens in that case is you get to a point where the pH drops back down below 9 and it starts to creep back toward 8 or 7 where it combines with other wastewater. All that dissolved sulfide starts to go back to equilibrium and some of it's going to come out of solution. So you can trap it, but you're not treating to remove it. It's still there. It can come back out of solution as the pH drops. So generally, if you do something like lime or magnesium hydroxide, that can keep the pH up for a while, but as it combines with more wastewater at different lift stations and different junction points, and the pH drops back down, that hydrogen sulfide is going to come back out of solution. So you're not, in that case, treating to remove, you're treating to kind of trap it in solution. Now, the other part that affects how much hydrogen sulfide releases besides turbulence and that pH is the temperature also. So both the temperature of the wastewater and the temperature of the atmosphere outside. So as you can see here on this chart, as the temperature increases, the amount of dissolved sulfide that will form hydrogen sulfide in air increases. So you can see here at the bottom of the chart, at half a part, you're probably going to have low levels, 5, 10, 15 ppm up to about 100 ppm from half a part of dissolved sulfide. If you're at 2 parts of dissolved sulfide, you're still going to start pretty low, so down around 50 or 100. But as the water temperature warms up, as the atmospheric temperature warms up, you can see that the increase in hydrogen sulfide happens. So you're going to go from down around 50 to 100 to well over 500 parts of atmospheric hydrogen sulfide that would be possible. Increase your dissolved sulfide level to 4 parts, 6 parts, and you can see you're starting much higher to begin with at low temperatures because of that equilibrium, and then even higher when the temperature rises and stuff comes out of solution and causes that. So it doesn't take very much dissolved sulfide to generate well more than 10 parts per million of atmospheric hydrogen sulfide. So if you are generating some dissolved sulfide, any kind of turbulence, any kind of temperature increase is going to strip that out of solution and lead to more odor complaints in your system. So one of the ways to remove hydrogen sulfide, so you have the dissolved sulfide in solution, permanganate is going to oxidize it, and it's going to oxidize it very, very rapidly in wastewater, whether it's at an acidic pH, so below 7, neutral pH at 7, or a basic pH where we're slightly higher up in the 8s and 9s. So we're going to oxidize it. The one thing you'll notice is as the pH increases, the amount of permanganate that you need does increase. Generally in wastewater, we're right around that pH 6 to 7 to 8. So we'll be right there toward the neutral level here, where it's about 4 parts of permanganate that you need for 3 parts of hydrogen sulfide. One of the benefits of permanganate is its reaction rate. So permanganate is going to react with hydrogen sulfide, and it's going to react pretty much instantaneously. So you add it to the wastewater. A lot of times we can do jar testing with it. Measure dissolved sulfide, add permanganate, stir for 30 seconds, measure dissolved sulfide, and show that all the dissolved sulfide is gone. So permanganate's reaction rate pretty much instantaneously with dissolved sulfide. You can also use another oxidizer like hydrogen peroxide. Hydrogen peroxide typically does need some reaction time, so you might need 20 minutes, 30 minutes in order for the peroxide, which is packaged oxygen, to react and remove the hydrogen sulfide. In the case of iron salts, you're not an oxidizer, you're a precipitation reaction. So you add iron salts to precipitate out iron sulfide. So you'll have dissolved sulfide, you'll add your iron salt. It's a precipitation reaction. Just depends on how you get contact and get that precipitate to form. But typically, if you're using iron salts, it's going to take slightly longer, up around the 40 to 50 minute mark for that sulfide to drop precipitously if you're doing jar testing or applications out in the field. So one of the benefits with permanganate is speed of reaction. If you've got an odor complaint and you want to treat directly at the source where you're getting it, you can treat right there and get the odor knocked down immediately. Oxidation versus precipitation for mercaptan destruction. So if it's not just hydrogen sulfide, if it's one of those other compounds of mercaptans, there's multiple ways you can treat. Once again, in this case, this was mercaptan concentration up around 35 milligrams per liter of parts per million. Iron salts, because there's an organic molecule attached to the sulfide, you can't really get a great precipitation reaction like you can with dissolved sulfide. So in this case, they were feeding 1,500 parts of iron salts, and they were only getting about a 10 part per million reduction in the mercaptan concentration. Peroxide will work. It will break down the mercaptan odors. They were using 420 parts of peroxide. You can see you go down from 35 down to less than 5, down to about 2. Permanganate, much lower dose, 177 parts. And we can get it down almost to less than 1 or to 0. So we get that reaction rate pretty quickly and much more oxidation of the mercaptan itself at a lower dosage than the peroxide itself. So there's a little bit of the chemistry. So what are you going to do if you do have odor complaints in your system? So the first thing is to do a wastewater odor survey. So systematically collect information about your wastewater system. And that can be where you're going to treat at. So how many odor complaints do you have in that area? How often or how frequent are those odor complaints? What's the flow rate of the wastewater that's there? What type of odor complaints do you have? Is it just the typical, hey, it smells like wastewater, rotten eggs? Do some monitoring as well. So what are the levels of complaints that you're getting? So obviously, hey, maybe we get a half dozen complaints from people in the area. So we go out and do some monitoring. And then the question is, what are the levels out there as well? Take that data that you've collected, organize, analyze the results to see where it's going to make the most sense for you to treatment out there in your system. So obviously you've got the first point where you've got odor complaints, right? You're getting complaints from the community or from your workers from being in an area. Well, then you can do odor monitoring. So there's two ways to do it. You can do spot checking with the hand pump that you see there on the far right, where you can just spot check to see, hey, what's the odor level I'm smelling? I can do a Drager tube or a different type of tube to determine it. I can do dissolved sulfide, which is a kit there in the middle where you can measure the wastewater's dissolved sulfide content. And then more common nowadays in the last 10, 15, 20 years is to put an odor log or an acrolog or some type of sensor out there and collect hydrogen sulfide data over a long period of time, typically at least a day, but maybe a week to 2 weeks, and then swap those monitors out because you can generate all that data to see when are you having the odor complaints, what's causing, or when does the odor spike out there in the system itself. The other part that you want to do out in the collection system, besides the odor log, is have a little bit of an overview. Okay, we're getting complaints in this neighborhood. So what's the wastewater that feeds that neighborhood or where that odor complaint is coming from? So obviously you can go back to your system drawings or you can kind of sketch it out on a piece of paper. So is it wastewater is being collected from houses and collecting at a lift station, and that first lift station doesn't have any odor complaints, but when we pump from that lift station downstream to a force main discharge point, where that force main is discharging, we're getting some odor complaints from the turbulence when it discharges. Or it's a sewer junction where multiple lines are coming in, and you do testing and 2 of the lines coming into a junction have no odor complaints when you do the testing, but 1 of them does have a lot of odor complaints. So then somewhere upstream maybe you're going to treat for that. And then at the headworks of the plant, maybe it's making it all the way to the plant and you're getting some complaints at the headworks of the plant itself. But collect that data, kind of backtrack to see, okay, what's feeding this? What could be the optimal way to treat for it? So out in the collection system itself, there's 2 things you're worried about. You're worried about those odor complaints, and you're worried about hydrogen sulfide corroding the equipment and the piping that you have out there in the system. So these are some pictures from different places we've been where they had part of the pipe actually corrode. So you can see the crown of the pipe in that case where it's corroded away from hydrogen sulfide. They were actually doing a sewer main replacement, and as they dug the pipe out, you can see that the crown of the pipe was missing in places. Around this tank here at this wastewater plant, you could see the corrosion just from hydrogen sulfide on the outside of the pipe where you're starting to see layers of the metal peel away and crack. So you can actually see it there as well. You flip over the manhole cover. So the manhole covers always look the same on the outside. They usually don't look like they corrode at all. You open the manhole cover up and you go down and you're going to either put an odor log in or you're going to do some sampling. So you're going to drop a sample cup down to grab wastewater, and you can clearly see that concrete does not look brand new. It's starting to crumble and flake. So you're seeing that concrete be attacked by the hydrogen sulfide sulfuric acid combination. The reason this is important kind of in a picture is the other thing is you can see kind of the rungs that there. Those are usually really good points for you to hang an odor log or some type of gas monitoring equipment. The issue is you want to make sure they're stable. So anytime that I'm going to put a hydrogen sulfide monitor below a manhole cover, I'm going to check, I'm going to give a really good tug on that rung to make sure that it's stable and it's held into the wall so that I can hang my monitor from it without fear of it falling down into the wastewater and getting carried down to the lift station or just completely lost or destroyed. So a couple times in my career of 26 years, we've opened manhole covers and went to grab those rungs and they've pulled directly out of the wall. So that can show you how bad the concrete's impacted in that case. So what can you do? Obviously, prevention rather than chemical treatment is the best way to go. So if you can move the wastewater as quickly as possible from the collection system through all those pipes and lift stations to the wastewater plant as quickly as possible with adequate flow velocities, you won't generate hydrogen sulfide. Wastewater that's brand new and fresh at a person's home typically isn't very stinky. It just takes time and collection in the wastewater system as well to chew up that dissolved oxygen and then start chewing on the sulfate to generate it. So try to minimize the detention time. Now that's not always possible. A lot of times the collection system is built for future growth. So the piping and the lift stations are built for, hey, we're gonna have 100 homes in this area, but when we first do the construction, there's only 20 homes. So everything's a little oversized. Wastewater sits much longer than it's supposed to. Now they can change, pumping rates, they can change levels in the lift stations to try to move that wastewater or pump it a little more frequently. But still, even at that point, the wastewater is going to sit longer. The other part, good housekeeping. So here in this lift station, you can see there's some grease that's forming. I don't know what it is about lift stations, but typically grease always tends to collect and float toward the side where you have the floats in a lift station wet well. So that can be an issue. The grease builds up, forms kind of a hard cap. It can collect on the floats, kind of impact them as well. So you want to make sure that if you've got a lot of grease issues, two things: make sure that you clean the grease out of those wet wells, whether you have a vacuum truck or other ways to treat to remove the grease. And then the other thing is a good pre-treatment program upstream. So tell homeowners, yeah, you're not supposed to dump grease down the drain. Have a good pre-treatment program as well for grease removal and grease traps at restaurants. So they have to have a way for them to remove grease rather than discharging it to your system. Just kind of good housekeeping on the front end to prevent putting that stuff out there into the system. But move that wastewater as quickly as possible to the wastewater plant so it doesn't sit and doesn't generate odor complaints. Out in the collection system, you have a couple different options for permanganate, and we'll talk about them. So you can kind of see this selection chart. Is it a gravity sewer? Is it a lift station, headworks, clarifiers, gravity belt thickeners, dewatering? So kind of a chart. Some things kind of make more sense out in the collection system. In this case, you'll see Totalox and CARUSOL. Both liquids can be applied with a metering pump. Some things will work, but they're not the first choice. So you could use something like CAIROX nuggets, where you just have a occasional odor complaint. So you throw some nuggets in a lift station wet well. They dissolve as they sink, and you get some treatment. But it's not a long-term treatment. It's kind of a spot treatment. In the plant, typically you're going to use things like CARUSOL as well, because you're doing continuous treatment. So out in the collection system, you really have two kind of options. You have CARUSOL liquid permanganate, and you have Totalox odor eliminator. So we'll talk about each of those. CARUSOL is a liquid permanganate, concentrated. You can buy CARUSOL, which is 20% active, or CARUSOL C, which is 40% active. Both of those are packaged from as small as a 5-gallon jerry can to a 55-gallon drum to a 275-gallon IBC. You can buy CARUSOL or CARUSOL C. And you can feed that product directly from the container itself. Totalox odor eliminator, it's a specialty blend, 1% permanganate, so it does have the distinctive purple color, and it's 40% calcium nitrate. Permanganate gives you the instant oxidation of hydrogen sulfide or mercaptan compounds, and then the calcium nitrate gives you long-term odor control downstream from the application point. So our first case study here, lift station in a municipality, 1.2 million gallons a day flow rate. And they were getting odor complaints from neighbors in the neighborhood and from a nearby soccer park that had been built next to the lift station. So if you ask yourself, generally lift stations don't look this nice. This was built right next to a brand new nice soccer park with multiple soccer fields for kids to play at. So they wanted the lift station to also look nice. So obviously a nice brick building there. They were having occasional grease issues in the wet well. So there's that picture again with grease. And I don't know why, but always attracted to the floats in the corner of the lift station itself. So they were getting odor complaints from people at the soccer park. Prevailing wind occasionally would be directly toward the soccer park. So when people were there watching their kids, they would get complaints. So a data logger was suspended in the wet well at the lift station to collect baseline hydrogen sulfide data. So you can see there's the odor log getting hung by a rope down into the wet well itself. Average in the wet well itself, about 14 parts per million in the wet well itself. And there was an occasional peak of about 80 parts per million. So in this case, they know they wanted to treat all the odor complaints were centered around this lift station. So we want to do immediate odor control and treat the wastewater right at this lift station. Now, as they drew out from this lift station, there was no upstream lift station where we could treat at. Everything that was feeding into this lift station was from homeowners, from standard wastewater from homeowners, and this was collecting all the wastewater from home. So no industrial wastewater, all just wastewater from consumers' homes. And just based on how long it was sitting at the lift station, it was generating odor complaints. They were also, because of the grease, they were having to go every 6 weeks to break that grease up, scoop that grease out of the wet well to remove it so they didn't have issues with the floats at the corner of that lift station. So what they decided, we need immediate odor control. So we're going to go with straight permanganate. And so they used CARUSOL liquid permanganate. And trial setup was 2 drums with 2 metering pumps. So the feed system decided, when we were looking at that hydrogen sulfide data from the odor logger, you could see that there was kind of an average amount of hydrogen sulfide and then occasional peaks based on, in the morning when people started to use water, the lift station would fill, and that would cause some pumping of the lift station, cause an odor complaint. And then when people got home at the end of the day, so between 3 and 5 o'clock, they might be cooking, they might be doing stuff. There'd be another influx of wastewater coming to the lift station that would generate a little higher peak as stuff stripped out. So they put those 2 pumps on timers. So one was kind of feeding all the time in the background, and then the other one would feed only during those times where they would see the increase in flow rates. So when the flow rate would pick up in the morning and pick up at the end of the day, the other pump would turn on and start feeding an additional dosage. So with the treatment going into the wet well itself, so we treated just before the wastewater would enter the wet well at the lift station, we were able to knock the average hydrogen sulfide with an odor log down to 0 ppm in the headspace. And then there'd be occasional peaks of about 10 parts per million of hydrogen sulfide. So there was still some peaks, but much, much lower than the 80 parts per million, no kind of background hydrogen sulfide. And that basically eliminated the odor complaints from the neighbors next to the lift station and people at the soccer park nearby. The other part with treatment with permanganate can emulsify and break down some grease compounds. So in this case, the cleaning of the wet well, which was about every 6 weeks, went down to about 3 times per year. So we were able, with the permanganate at the low dosage going into the wet well kind of on a continuous basis, to kind of break up and destroy some of that grease. But not completely eliminate it from the wet well itself. So they still did some cleaning a couple times a year, but much, much less than they had done before. So there's a case where it was immediate odor control, so we need concentrated permanganate. The next we'll talk here about is Total Ox Odor Eliminator. So this has a little bit of permanganate for oxidation, but the primary use is nitrate salts for sulfate reduction. So prevent the bacteria from chewing on the sulfate, they'll chew on the oxygen off of the nitrate compound. So those bacteria out in the collection system really want dissolved oxygen. If they don't have dissolved oxygen, they'll chew on the nitrate. If they run out of nitrate, they'll start chewing on the sulfate. So you're just giving them kind of an alternate food source. Kind of the general rule of thumb in this case is you need 2 to 4 gallons of the permanganate nitrate blend per pound of dissolved sulfide to remove. Now, typically what the treatment goal is, 0 milligrams per liter of dissolved sulfide in the effluent. So where you're having your odor complaint, you'd like the dissolved sulfide to be at 0, so you're not having anything that can strip out. And then if you are trying to maintain nitrate residual through maybe 1 or 2 or 3 lift stations, you might want to see some nitrate residual. So if you're feeding at 1 lift station and you've got to go through 2 lift stations where you have odor complaints, your first lift station, you'll probably have some nitrate residual and no dissolved sulfide. And then your final one, where you're still getting odor complaints, you'll want to have very little dissolved nitrate and no dissolved sulfide at that point. So it's just a matter. You can feed it multiple lift stations if you want to, but sometimes it's easier setup-wise to feed it 1 and carry it through a couple lift stations. Or if it's a force main, you feed it the front of the force main and you want to make sure that you don't have any dissolved sulfide at the discharge. Now, as temperatures warm up, you typically might have a slightly higher dosage, bacteria are more active. The other one that's really the biggest one is longer detention time. So the longer that wastewater sits at the wet well, the longer it takes for that wastewater to travel through the force main to its discharge point. That bacteria is going to have longer to be looking for a food source. So in that case, longer detention times typically require higher dosages. So if you're talking about, the wastewater takes 6 hours or 8 hours or 12 hours to get from point A to point E, it'll be toward the lower end of the dosage. If at that lift station with that force main, you're talking, hey, for the wastewater to turn over at this lift station, it's 20 hours or 30 hours before it starts moving downstream. So it's sat for a long time, it's going to be toward the higher side of that dosage. So just one of the things to keep in mind, detention time does matter because the longer that bacteria has, the more nitrate it's going to consume. So this collection system lift station was a very large southern city, and they were completing a rehab project on a 54-inch gravity sewer line that was along the river. Now, that rehab project, because they were bypassing, they went through a brand new nearby retail district. So it went by a museum and all the shops and outdoor dining in the downtown area. So what they found is while they were doing this rehab project and they were bypassing the wastewater, they were getting a lot of odor complaints as the wastewater moved to that area. What they found was there was a 42-inch outfall and some downstream 90-degree turns in the 54-inch line, and that was causing enough turbulence to strip sulfide out of solution and causing some odor complaints. So the city itself with an engineering firm had done some odor complaint profiling. So they did some odor loggers that were installed in 4 manholes along the line. Itself. Peak hydrogen sulfide levels you can see here in the chart. So the 4 different manholes that they did monitoring at. Average sulfide, hydrogen sulfide, 3 parts, 5 parts, 5 parts. The real bad one was at 16 parts for average. And then some peaks in the hundreds. So you're getting peaks, and those were typically, the peak is what's kind of forcing the sulfide out of the manhole cover to the atmosphere because there is a little bit of venting in a manhole. And so they were getting odor complaints from that. So the city was looking at a quick solution for the problem. The one thing they did know is if you seal the manhole covers, that's just trapping the hydrogen sulfide below the cover, and you're going to start destroying all that infrastructure from the hydrogen sulfide below the manhole cover in that case. So what they were looking for was a quick solution for the problem. They really wanted to eliminate those odor complaints in that retail district. So they decided, obviously we're doing a rehab project. It's possibly going to be 1 to 2 years for a rehab project. While we're doing this rerouting, we have an issue. So we want a temporary setup. So at the lift station upstream of all those manholes, they had plenty of space to put in a temporary bulk tank. So brought in a Baker tank and set it up in portable containment. And then had metering pumps in a Rubbermaid hut tied together. So they had 2 pumps, so they had redundancy. They could feed with one, and the other one's a backup. And what they did during the feed system was they would switch every week back and forth between one pump or the other. Both pumps could do as much as they needed, but it gave them the confidence that we always have a backup pump, and something happens to one pump, we've got another pump. The other part was they had remote telemetry on the tank as well. So they could tell what the level was in the tank. So that was a way for them to verify the pumps were pumping what they wanted them to. And then that was also the way that they could determine, along with us at Carus, hey, it's time for a reorder. So the tank could hold more than a full tanker truck, which is 4,000 gallons. So in that case, as they got low, they could say, hey, it's time for us to place an order based on the tank level, get the order in, and then refill, and then look at that monitoring remotely. So monitoring after we started feeding at the lift station itself, the hydrogen sulfide at the two worst, we got about an average of 14 instead of the 15, and then an average of 6 instead of the 5, but we were seeing the same data they were, and then the peaks were about the same too, right? 150, 190, 200, we were seeing it. So initial month that we started up the system, they were getting about 5+ odor complaints per month from people in the downtown retail district and from the museum that was downtown. So system was set up. We initially started feeding at 100 gallons per day to the wastewater flow itself. Average hydrogen sulfide dropped down to 1 parts per million at both manholes, and the peaks well below 200. Now we're at 25 and 5, so much, much lower levels. The first month that the system was started up, we had 1 odor complaint down from the 5 they had the month before. So significant decrease, but still had an odor complaint. So what they decided was, with the city council and the wastewater plant people, we really would like no complaints. So yeah, it went from 5 to 1, but we still had 1. We'd like to kind of drive it to 0 complaints. So increase the feed rate going into the wastewater from 100 gallons per day to 125 gallons per day. And the average hydrogen sulfide dropped to 0. And the peaks were only 1 peak parts per million. So that drove all the odor complaints away. The rehab project took about the full 2 years for them to do. So they had thought between 1 and 2 years, and it actually took a full 2 years. During those next 24 months, they only had 2 more additional odor complaints in those 2 years. So knocked them down completely, almost completely gone. At the end of this, the rehab project was done. They were able to reroute the sewer back the way they wanted to. And with the rerouted sewer, they didn't require odor complaints. So this was just a temporary setup for the rehab project. And then once that was done, as wastewater moved in its normal flow pattern through the area, they got rid of those complaints completely. So other options for permanganate, in this case, would be solid permanganate. These would be nuggets. So you'd use these out in the collection system. You use these kind of for spot odor control. So you can see a picture there. They're kind of chunky permanganate chunks available in pails. And where you would use these, you have a manhole that has some issues with odor complaints, or a lift station wet well that has complaints, but generally you don't have complaints all the time. You'd go out and you'd scoop out some of those nuggets out of the bucket and throw them or broadcast them into the lift station wet well. They're going to sink, react, and generate, destroy the hydrogen sulfide at that application point. The other time we see these out in the collection system is if you have a wastewater lagoon that has gone septic or has some odor issues and generally doesn't. You can go out and treat with the nuggets, broadcast them from the shoreline, so throw them out into the lagoon, or sometimes we've seen people go out on a boat and then just as they're going out in the boat, just broadcast them by hand across it. They're really just a spot check for odor. You don't have normal odor complaints, you've gotten some, so you want to do something, you can throw the nuggets out. Very, very low tech. You're broadcasting them for the odor control. The nugget's large enough that as it sinks, it reacts and removes the hydrogen sulfide. You do want to be careful if it's windy conditions. They can be dusty, so you'll want to make sure you're wearing a little N95 dust mask if it's a windy day, or if you can avoid the windy day, feed them on a day where it's not windy, so when you're broadcasting, you don't generate that. Sometimes with lagoons, it's always windy, so they might switch and make a liquid permanganate solution or use CARUSOL directly and go and spray that on the surface of the lagoon and do the treatment that way. So very, very low tech with the nuggets. So at the municipal wastewater plant, so we're out in the collection system, we do have the options for CARUSOL, we have the options for TotalOx. You move into the treatment plant, and do odor control. So you've got the headworks, you've got sedimentation tanks, you've got clarifiers, you've got sludge dewatering. So lots of different places where you can have odor complaints where you might want to treat. Come back to our selection chart, you'll see that at the headworks, it could be CARUSOL, CARUSOL Plus, or gravity belt thickeners, dewatering. It could be those products too as well. So CARUSOL and CARUSOL Plus are both liquid permanganates. CARUSOL Plus is a combination product. And then you also could use CAIROX nuggets if it's just a small application, like in a clarifier that's gone septic at your plant. So our case study here, Headworks hydrogen sulfide case study. So this was a plant that actually had a concern, small wastewater plant, about 0.95 MGD, so 1 MGD, and primarily all residential wastewater. The wastewater plant was in the middle of a neighborhood, and so they were getting some odor complaints from people in the neighborhood, but they also were having worker safety issues. So wastewater would come into the wastewater plant, and there was an equalization tank prior to it going to coarse grit screening removal. So plant staff would have to come in and they would work on the screens and clean the screens and the grit for the grit removal. And they would have hydrogen sulfide levels in the room of about 40 to 100 ppm, so way above the 10 part per million level. So what they would do when they would go into the room is they would open the door to kind of ventilate it. And they had a ventilation fan too. They would turn that on as well. And so what that would do is it would, as the sulfide had built up in the room, it would vent it to the atmosphere, which would then cause complaints in the neighborhood. But then it allowed the level of hydrogen sulfide to drop lower in the room. So it was safe for the workers to be there. But you're also now causing the odor complaint in the neighborhood as well. So the manager at the plant says, hey, can we do something to treat at this point? And I'd love to be below 10 parts per million without having to turn the ventilation fan on, right? So I'm not venting anything to the atmosphere to cause odor complaints in the neighborhood. And ideally, hey, could I get less than 5 parts per million in the room without turning the ventilation fan on? So they chose CARUSOL liquid permanganate into the collected wastewater. Initial dose very, very high. So typically in collected wastewater, we're usually down around 10, 25, maybe as high as 50. But because the sulfide level was so high and there was that basin, wanted to treat and knock that wastewater odor out of that equalization basin very quickly. So the dosage started at 100. So after 2 hours, sulfide in the room dropped from 20 to 25 on the day we were there to less than 5. So then the permanganate dosage was cut in half. So we cranked it back after we turned over that equalization tank, and sulfides dropped in the room down to less than 2 to 3 ppm. So we're below his 5 ppm goal. And then that same day, we were able to turn the dosage all the way down to kind of a more normal dosage of 25 milligrams per liter for the wastewater coming in, and kind of maintain that average of 2 to 3 parts per million in the room itself without the ventilation fan running. So, you know, kind of slug dosed it to treat everything, kind of get everything knocked down, and then eventually got to a maintenance dosage of 25 milligrams per liter to keep the hydrogen sulfide below 5. So the workers could be in there as far as the OSHA standard. They didn't have to turn the ventilation fans on to generate the odor complaints in the neighborhood either as well. So fixed it with, you know, one product, fixed both issues. So our last case study here, very large Midwestern plant, 250 MGD case study that watered primary biosolids. About 110,000 gallons of biosolids on a daily basis was being dewatered on belt presses. They had 6 belt presses, 110 gallons per minute going to each belt press, and started at about 3 to 4% solids going to the belt press. So they were getting some complaints. Hydrogen sulfide in the room around the belt presses was 5 to 8 ppm, so below the OSHA standard of 10. But if they walked up onto the platform next to the discharge here, where you can see the picture on the top where the sludge is coming out on the top of the belt press, it could be as high as 90 to 100 parts per million if you're directly over the top of the belt press. So there was some exposure concerns. and it's still at 5 to 8 ppm was pretty strong in the room itself. So they chose to use dry permanganate over liquid permanganate for the initial setup. In this case, it was a drum inverter system, so you can see the drum on top of a feeder, and the permanganate was injected. So permanganate mixed in with water and then going to the injection point for the sludge line going to the belt press. Full scale dosage going into the sludge line, somewhere between 60 and 85 parts per million of permanganate going into the 3 to 4% sludge for odor control. Now this was in the basement of the building, so sludge came from the sludge tanks to the basement of the building. We treated after the sludge pumps, and then the sludge was treated with permanganate, and then it went in the pipe upstairs to the 3rd floor. So we're in the basement, it went through the 1st floor and then went up to the 2nd floor, and then the polymer was added directly before the belt presses. So we had a little bit of contact time before the polymer was added. As we started treating, the hydrogen sulfide was reduced from that 50 parts per million that you saw earlier down to less than 2 parts per million, and the hydrogen sulfide in the room to less than 0 parts per million. Now, as we were treating, this was mostly primary biosolids. They kept track of 2 things. So one of the things we noticed is when we started treating to remove the dissolved sulfide, we were able to turn back their polymer usage from 75 pounds a day per press to 33 pounds per day. And we were still getting good cake solids. We saw an actual cake solid increase of about 2.6% coming off the belt press. So we went from about 24% to about 26% cake solids coming off the belt press. Typically, you see polymer reduction in cake solids treatment if there's a lot of hydrogen sulfide and it's mostly primary wastewater. Treating that wastewater to remove the dissolved sulfide and getting some permanganate byproduct manganese oxide in typically can sometimes help lower your polymer usage and maybe see some increase. Long term, they've had the dry system for many, many months, but they had to switch the drums out. They were running water that they were paying, so we have to make the dry permanganate down into solution to inject it. So what they decided to do long term was move to bulk liquid permanganate. They brought in totes at first and fed from totes directly to the application point, and then eventually moved to a bulk tank and then the same metering pumps to do the application, which just eliminated a lot of operator time. So when you had the dry and the water, on the system, you'd have to change it out more often. And when they went to the totes and the liquid bulk tank, they don't have as much maintenance time there. So in summary here, locate the sources of odors that you have out there. And once you found out where they're at, can you minimize the detention time? Can you have good housekeeping so that you're not generating that odor? So move that wastewater as quickly as possible. Make sure there's not grease, there's not other biosolids out there in the system, and get those to the finished application point. You do have treatment options. So out in the collection system or in the plant, and you have immediate odor complaints, you can use CARUSOL liquid permanganate, whether it's 20% or 40%. We've used both in the collection system and at the wastewater treatment plant. In the collection system, if it's long-term odor control, so it's at a lift station and then maybe another lift station or maybe a force main discharge, you've got long detention times, you could use Total Ox, which is the combination of permanganate and nitrate itself. You can't use the Total Ox in the treatment plant itself because nitrate interferes with your bacteria in your treatment plant, and what you'll end up generating is some nitrogen gas, and you'll get floating sludge in your plant. So Total Ox, 100% out in the collection system only. You can't use that in the treatment plant itself with your clarifiers. And then whether it's CAIROX potassium permanganate nuggets, those can be low odor levels. You have an initial complaint at a lagoon or a clarifier or a lift station, you can go out, spot check those and discharge those and treat for kind of the non-routine odor complaints that you have. And then there's CAIROX potassium permanganate. You can have a dry to liquid feed system in place of the CARUSOL at the treatment plant because you do have those utilities. So with that, there's my contact information, our phone number, the Carus website, sale and marketing contact information as well. So we'll look to see what other kind of questions you guys have and answer a few. So can you use permanganate for a large biosolid sludge tank that has no mixer? So the issue with something like that is you're going to need something to get the permanganate to react. So if it's a large tank and there's no mixer, is there a recirculation pump in it? Is it not odor from the tank itself, but when you move the sludge out of the tank to somewhere else? So if it's like a clarifier or it's a large sludge tank, nuggets would be one thing to try. You could broadcast the nuggets. Since they're larger and heavier, they will start to sink and you'll get some reaction. It really just depends on how heavy the sludge tank is. So like in a clarifier, you're 0.5%, 1% solids. The nuggets are going to sink pretty rapidly and they'll do that treatment as they sink. If it's a tank where you're 3%, 4% solids, they'll sink, but they won't sink all the way as they react because it's going to take a lot longer for them to sink. You do need to get some contact between all the solids or sludge in the tank with the permanganate itself. So we've seen ones with no mixers, but they recirc the tank so they can pump the wastewater sludge out and back into the tank, and they'll treat in the recirc loop as a way to kind of treat it. So. Second question. So how would you take care of a spill of permanganate? So yeah, we have a ton of safety information available for permanganate. First thing, depending on what type of product you're going to have, if it's a CARUSOL liquid permanganate, 20% or 40%, you typically will dilute that down to less than 5%. So you dilute the application and then you'll dilute it first and then you can neutralize it. Lots of ways to neutralize it. Kind of the most common that people use is vinegar and peroxide. So we use food grade white vinegar, 3% hydrogen peroxide, both things you can buy at the local grocery store. We mix those together in a 50-50 ratio, or sometimes we add about 1/3 of a part of water to it. And then you can neutralize diluted solutions of permanganate. So what'll happen is that vinegar peroxide solution will turn permanganate from permanganate to manganese dioxide, so it'll turn brown. And then if you continue to use the cleaning solution, the manganese dioxide will go to soluble manganese and you'll completely clean the stain. A couple more questions that have come in. So the formulas for the reactions for hydrogen sulfide showed potassium permanganate. However, CARUSOL is sodium permanganate. Do they work the same? Yeah, the reaction's actually from the permanganate itself. So potassium permanganate is KMnO4, sodium permanganate is just NaMnO4. So it's the same ratio. It ends up being the same ratio. So potassium permanganate and sodium permanganate react the same way because it's just the permanganate that's doing the reaction. All the potassium or sodium determines is the solubility. So potassium permanganate has a max solubility at room temperature of 5%. Sodium permanganate, when you swap that ion out, has 20% and 40% concentration that you can ship. So if you're picking a permanganate, if you want to feed a liquid, it's easiest to ship 20 and 40 because you're not shipping a lot of water to do that application. If you want to make up solution on site, you can buy the dry, but then you're going to be making less than a 5% solution on site. Typically, most people make a 3% with potassium permanganate, but all the reactions, all the chemistry are the same. So what is the relationship of polymer usage in the wastewater belt press case study in relation to other uses of CAIROX? So what we've seen over the years with sludge dewatering, and especially if it's primary sludge. So primary sludge doesn't have secondary waste activated sludge in it, so it's not all bug bodies, it's mostly just primary biosolids. If it's very stinky, high hydrogen sulfide levels, high dissolved sulfide levels, what ends up happening with the permanganate is we knock the sulfide out and we're generating, because we're in that 50, in that case study you saw 50 to about 85 parts of permanganate, we're generating some manganese dioxide solids from the permanganate reaction. So those manganese dioxide solids have a slightly negative charge, so they grab onto stuff. And so you start to see some coagulation with just the permanganate itself. What that does is, because we're already kind of clumping stuff up after the permanganate reaction, the polymer works slightly better because you've already got some solids formation going. So we see it sometimes in primary wastewater solids. Where we don't see it is if it's secondary waste activated, so that's always, you know, a lot of bug bodies. Those always dewater poorly. Permanganate doesn't help with that because the bug bodies are kind of holding onto that water. They don't release it. So you don't see the benefit there with the polymers. We see kind of the same effects sometimes in drinking water as well. In drinking water, if we treat with permanganate, we generate some manganese dioxide. If there's also some hardness and alkalinity in the water, we'll actually start to see floc formation just with permanganate prior to us adding the coagulants. So it's just one of the benefits that we get as the byproduct of manganese dioxide generating those solids. So with that, I didn't get to all the questions, but thank you for all the questions that you guys all sent in. I will reach out to each of you to answer any questions that you may have, follow up with you. If you want a copy of the slides or want to share a link to this webinar, it is recorded. You'll be able to do that as well. So thank you all for your time. Hope you guys have a great day.